Hey everybody, welcome back. This is Machine Learning version 2, Electric Boogaloo. We're going to get into a lot more detail on a few new tricks, but before we do that, as always, let's take a look at what's coming up. So assignment 2 is due this Friday, and if you have any questions, please let us know. This is the first time you're actually doing something with data, so I think it's kind of exciting. So along the lines of actually doing something with data, please do start to discuss with your group if you're going to do something extra credit-wise. Okay, if you are going to try to attempt some sort of actual analysis, not just the report, it's time to organize that. Now, it can be the case that some members of your group are not feeling comfortable doing that because they haven't had the programming experience or whatever. So if part of your group is interested and part of your group isn't, please try to find an equitable way to divide up the work. Okay, maybe the people who are not doing the extra credit bit are more working on the report itself, or maybe there's a way to divide up the programming so that everybody gets a little taste of it, no matter what their level. So just FYI, I think that while there might be disagreements, there are ways that groups can work this out. Okay? Next item of business is that several people contacted me and wanted to get access to the right answers for exams and quizzes. To be honest, I hadn't realized they weren't already available, so that should now be fixed for you, those that want to review their past performance. And as far as the grades on assignment 1, it has been slower than I had hoped. I apologize for that. At this point, about half of them are graded. So that's affecting several things, and I will try to make sure that we get this out, if not in the next couple of days, certainly by the end of this week, because it's just, I realize that it's very frustrating for you. All right, let's get into it. That's where I wanted to be. All right, Machine Learning 2. So today we are going to take a look at the process of actually building a model and running it. So we're going to do that both theoretically and give you kinds of examples of how to get after that. And we're going to have a little deep learning fun because I know that that's the buzzword du jour, and everybody would like to know a little bit more about that. So let's take a moment, remind ourselves what we have already learned about machine learning. Okay, it's prediction. We're going to use it for prediction basically as data scientists. Just FYI, there are ways to use machine learning for building models and looking at modeling, but realistically, most of the time you're just trying to find out, can I predict the next thing? All right, so the elements we've talked about a little bit are data partitioning into training and test set. We're going to see a lot of that today because we're going to talk about the process. Right? We're going to try to select the right model type and maybe parameters in the model. And we're also going to try to select features that are transformations of the data or subsets of the data that allow us to efficiently solve the prediction task. And finally, once we've done the prediction, we have to figure out how good was it. And so we need some sort of assessment of the prediction. So we're going to start off with a very nice little worked example from the internet tubes. There's a thing about predicting whether a home is in San Francisco or New York City, right? So if we have a bunch of data that you might find about real estate listings, things like price, square footage, amenities that are at the particular location, you know, how many bedrooms, how many baths, stuff like that, maybe a few other things. and you were given the task of predicting whether the home is in San Francisco or New York City, what would you do? How would you approach this? So I'm going to give you a minute to think about your answer. And I'm also going to say right here that basically tonight I'm probably not going to put up these Google Forms. It just was a lot of hassle when I was mostly asleep last time. So these questions, they're, the kind that you can think to yourself and answer to yourself. All right. So I hope that you said something like classification. You could potentially see it as a clustering, but that's relatively less sure that you're going to get a good answer with things like that. Whereas a classification task is how we're going to address it right now. But definitely not A or D. All right. So what features distinguish a house in New York from one in San Fran? Well, obviously, if you were looking at a property listing with your own eyeballs, you could actually do this task, right? You would probably just look at the property listing online and see the part where it says what city it's in. But the deal here is that we just need a good example that we can take data which is easily available and try something that maybe doesn't make a lot of sense, figuring out where things are, just to show you how we build a model. So if you look at all the data that's available from one of these online real estate listing services, you will find there's many different things, but one of the ones that best distinguishes San Francisco from New York City is altitude. Right? Altitude, like how many feet above sea level you are. So it turns out that a home above 73 meters basically is going to be in San Francisco. Why is that? Well, so this is a representation of the height of a given house, right? So here are ones that are very close to sea level, and here are ones that are a little higher, and so on and so forth. Well, San Fran has some big tall hills and mountains, and New York City has some skyscrapers, but it turns out they're a lot shorter. So with New York City in the blue and San Francisco in the green, we can easily see that anything above here is very clearly a San Francisco house. All right. Well, the thing is that you don't get a very good idea of, you don't get a very good performance if you're just using the height, the altitude of the real estate listing. So it looks like also if you look at the dollars per square foot, that New York City, at least when this little thing was made, was a little bit more expensive. And if you look at the data here, get my face out of the way, New York City dots are all lying out there, right? San Fran dots tend to be on the left side of that line I'm drawing right here. Well, what's going on here? We have altitude on this axis, dollars per square foot on this one. So we can see that there is some patterns that might be useful for distinguishing whether this place is in San Fran or NYC. All right? These dimensions that we're having here, altitude and dollars per square foot, these are our features. They are variables we're going to use to predict with. All right. So it seems clear, like I basically did, that you could draw boundaries and you could see where the green is San Francisco and the blue is New York City, and you can find regions where you're pretty sure of your answer, and this region on the lower left of the graph where maybe things are a little less clear. So it turns out this data set also has a lot of other dimensions, and we can use all of them to try to make better decisions about where this home is located. Now, it's a little bit hard maybe for you to squint at these. You can kind of see that there's patterns in these different 7 variables, but different features. But the machine learning system has this advantage that it can do this without really too much cognitive effort, right? It's a pretty simple algorithm that just runs through the data one variable at a time, and it looks to see if it can make a decision based upon each of those variables. Okay? So how can we do that? So if we want to see about the 73 meter threshold, we can try to look at not just where things are, but where they're spread across. Okay? So the highest home, as we know, is in 73 meters in New York City. And the histogram lets us see where the density of these different locations, of these different altitudes is. So we can use essentially a glorified if statement called a decision tree to find out where we should split the data into SF versus NY. So we're looking for a trade-off. We want to pick a point, either maybe that always hits all the San Francisco homes that it can, and maybe includes some New York City homes that accidentally get called SF. Or we could pick a point where what we want to do is make sure that absolutely no New York City homes are misclassified. Those are different things, and they're going to get a different trade-off. Or you can try to do something like minimize the total number of errors you make, but that might penalize one or the other of the categories overly. Okay? So if you set this threshold we've been talking about, 73 meters, 242 feet, then we're going to get some things that really are labeled as, everything that's labeled as San Fran over here is truly San Fran, right? There's 47 of them. But those things that are labeled as underneath this threshold, right? These are a mix of correct in the blue, and this is wrong in the green. Those are incorrectly labeled. They are false negatives. They are actually supposed to be San Francisco, but we called them New York City by this threshold. Okay, so a split point made to capture every single San Francisco home will include a bunch of New York City homes as well, like we were talking about. Okay, now in this case, these ones are wrong. So these are false positives. They were supposed to be San Francisco, all of them San Francisco, but some of them are NYC. Right? So that's when we set our threshold down here at 0. Right? All right, so we can also pick a threshold, 91 feet, which gives us a mix of false positives and false negatives, but the overall number of incorrects is the lowest we can get. Okay, so we've split based on altitude. Now let's go ahead and take a look at what else we can split on that produces better results. Okay, so we can split on dollars per square foot and can keep on going from there. So at this point, I am actually going to try to run this as a little demo. Let's see if we can actually use the live version of this. So I would have to do that and go over here. All right. So here's our lovely tree. So we can scroll down and see that we can add additional forks to this decision tree Each time we can add a new variable. We already did elevation. We can do price per square foot or just dollars, right? Straight up and without the square foot normalization. And we can split each one of these things at an appropriate threshold, which is going to give us the fewest misclassifications. Okay? So by splitting one layer deep, we get to 84% accuracy. If we go another layer or two deep, we can get much better. Adding all of these different variables, the year built, the price, so on and so forth. And we keep splitting and splitting and splitting, and we can get to 96% accuracy. We could even go all the way up to 100% accurate. How do we do that? We keep splitting until at the ends of one of these bits, we have just one unit, one property unit. And a given property unit is only going to be in San Francisco or in New York City in this data. So once we get to just one unit in the edges of this tree structure, we are inherently going to be 100% accurate on the training data. But being accurate on the training data is no guarantee that you will still be good on new versions of this data. Right? Somebody pulls out a bunch of new properties and throws them at your feet. You may not classify them correctly. Okay? So, at any rate, just to give you a little feeling of decision trees, when you get all the way out to the end of trees, the things on the ends of trees are leaves. So that's what we call it when we split it all the way out to individual properties. All right, so let's understand how it works to make predictions. All right, we had a bunch of training data. We used it to determine the splits that we are going to use to train to make this decision tree. How we're going to use different variables and classify things as being in one or the other. All right, so by setting up this all the way to the end of the leaves, we can get 100% training accuracy with all of the, when I take my face away, I can't, haha. All right, well, whatever. So with all of the training examples perfectly classified. All right, but what really matters is that once we train this tree, we can get brand new data from the same process. More real estate listings happening now in 2020. All right, let's see if we can classify them accurately. So we get brand new data into our created tree. The tree was created on the training set, and we are testing it on a totally separate test set. And it turns out that we can't get anywhere near our 100% accuracy. We get up to 89%, which ain't bad, to be honest, but definitely not 100%. What has happened? Why were we able to do 100% on the training data? Well, our model was set up to do as best as possible on what it was trained for. And because it was set up to train on this, it's learning unique features of this data set that are really just random noise, right? It's really just what happened randomly in our data set, okay? So we know that in the future, with new data, we will get different kinds of unique noise, and our model is not going to be up for that. It's going to have been overfit to the unique properties of our training data. It's not fitting pattern, it's fitting noise, okay? So this kind of thing happens whenever we have a very powerful machine learning algorithm, like a decision tree. Decision trees can definitely learn very, very difficult problems, okay? And if you give it data that it's going to get better and better on, it's going to learn, as it says here, to make distinctions that don't make a difference. And in that case, the model will not accurately be able to It will not do as accurately at new data that it's never seen before, even if that new data comes from exactly the same process. All right, so that is my little live demo. So we know that we need to watch out for overfitting. Okay, so I want to take a short little break, give you a chance to stretch your legs maybe, and I will come right back with more machine learning in part 2. All right, see you soon.